Okay, so now let's take a look at just some basic functions and talk a little bit about limits. So here we have x squared plus 3x plus 4. It's a continuous function. It's defined over the entire domain of the set of real numbers. And any limit can be evaluated just by plugging in the value for x. So if we wanted to know, for example, what is the limit of this function as x approaches 0, well, here we can see that f of 0 is equal to positive 4. And we can see both of our limits, our left hand and our right hand limits, are both approaching 4 as x approaches 4. So as the x approaches from the negative side or the positive side, the limit is just going to be 4. So both limits are the same. This is an easy limit to evaluate, again, because we have a continuous function. Okay. Let's take a look at this function. We have 1 over x minus 1 plus 2. So it has asymptotes at y is equal to 2, and that's because of this thing right here, the plus 2. And it also has an asymptote at x is equal to 1, and that's because of this thing here. We have an x minus 1 in the denominator. So the function is not defined when x is equal to 1. And the limits as x approaches positive 1 from the left side or the right side, the limits are going to be positive and negative infinity, and they're diverging, so this function has no limit at x is equal to 1. As x approaches positive infinity, we can see that the value of this function will approach 2. And that makes sense because as x becomes a very large number, this basically becomes 0, and this gets closer and closer to 2. And we can see as x approaches negative infinity, the value of this function also approaches 2, but from the negative side. Okay, now we look at a very different kind of function. This is the greatest integer less than or equal to. So for example, if x is equal to 0.54, the greatest integer less than or equal to that is 0. So the value of the function at 0.54 is 0. As soon as we get to x is equal to 1, the value of the function jumps up to 1, and the value of the function stays at 1 until we get to 2. So we have a point at the end of this segment here, but it's open at the right end of the segment. So let's take a look at the limits now. So as x approaches 2 from the left and the right hand side, we can see that the left and right hand limits are staying the same. The left hand limit is staying positive 1 and the right hand limit staying positive 2. And that's going to remain true. And so this function has no limit at x is equal to 2 because the left and the right hand limits are not the same. On the other hand, when x is equal to 2.48, let's say, then our left and right hand limits are both equal to 2. So this function does have a limit as x approaches 2.48. So when x is any integer value, this function will not have a limit, whereas any other value, it does have a limit. And that can be evaluated just by plugging the value of x into the function. Okay, so here's a function that looks exactly like the line y is equal to x minus 3, except that it has a hole at x is equal to 2. So the function is defined everywhere except at x is equal to 2. The limits, on the other hand, as x approaches positive 2, we can see that the limits are approaching negative 1. And so this function does have a limit at x is equal to 2, even though it's not defined at x is equal to 2. And the reason is, as x gets closer and closer to 2, the left and right hand values approach negative 1, and we can get them as close to negative 1 as possible. So the way we would evaluate this limit is by plugging the value of x is equal to 2 into just this part of the function here, which would yield the value of negative 1, which is the limit as x approaches positive 2. So here's another function, sine of x over x, And so what makes this difficult is that both of these approach 0 as x approaches 0. So this one is difficult to evaluate. Graphically, however, what we can see is that as x approaches 0, although it's not defined at x is equal to 0, the value of the function is very close to 1. So the limits as we approach x is equal to 0, the limits from both the positive and the negative side approach positive 1. And so this function does have a limit at x is equal to 1. I'm sorry, at x is equal to 0, even though it's not defined there. This would be an example where it would be easier to evaluate that limit graphically than it would be algebraically, although we will learn algebraic methods to be able to evaluate that limit. Okay, so here's a function. It's defined as 0.5 x plus 2 at every point except when x is equal to positive 1, at which point the function evaluates to when x is equal to any value except positive 2. When x is 2, the value of the function is 1. So we have a hole in this line here at x is equal to 2. The limits, on the other hand, as we approach from both sides, the limits, positive and negative, are approaching the value of 3. So even though when x is equal to 2, this function has a value of 1, the left and right-hand limits both have values of 3. So this function does have a limit at x is equal to 2. That limit is 3, even though f of 2 is not equal to 3. F of 2 is equal to 1. Okay, this is a function that's continuous. The only things that are of note are that as x approaches negative 3, you can see that our limit, the value of the function is approaching negative infinity, and then the function is not defined below a value of x is equal to negative 3. On the positive side, the value of the function just gets larger and larger, so there's no limit. Okay, we'll look at some other functions later.